So in this video, I'm going to show using first principles that the power rule of calculus does in fact work. The power rule says that if we have a function x to the n, where n is some real number, then we can take the derivative, which is just that exponent, times x to the power of n minus 1. Now to do this, we always start with our first principles definition, which I've already written out. And to do this, let's start by rewriting this in terms of our function x to the n. So instead of doing, we're going to start with the limit as h approaches 0. Instead of f of x plus h, let's write that as x plus h to the n. I'll write my h is a little more clearly just to make sure this is totally clear. And then we have minus x to the n. Now the tricky part with this is that when we expand this, it's going to look drastically different depending on what our n is. It could be, if it were n equals 1, it would be very simple. But if it were n squared, it could be something a little bit different. So to help us out a bit, we're going to use a bit of an analogy here. Just look generally what happens. Instead of talking about x plus h's to the power of n minus x to the n, let's call that a and b. So instead of using x plus h, let's use a instead. And for x, let's use b, just because we know a and b can represent two totally different things. So let's look. Generally speaking, let's look at a couple of examples. Let's say if we had a squared minus b squared. Let's suppose that n is equal to 2. We know that would be a minus b, a plus b. If we had a cubed minus b cubed, hopefully you remember this from advanced functions. If not, it's a minus b times a squared plus ab plus b squared. And as it turns out, the general rule is that when you have a to the n minus b to the n, the way that works is you have a minus b, and then we have a to the n minus 1 times b to the 0 plus a to the n minus 2 times b to the 1. And as we keep going through the sequence of terms, we don't know how many there are exactly. It'll change depending on what our n is. But you're going to notice that the exponent on the a tends to go down by 1 every time, and the exponent on the b tends to go up every time. So we keep doing that until we get to the end. And our very last term, or the last two terms, I'll do the last couple of terms. That's going to be a to the 1 times b to the n minus 2, then a to the 0, or 1, times b to the n minus 1. So in fact, when we look at a to the n minus b to the n in general terms, that's actually what it looks like there. So let's use that form and let's rewrite what we have here to help us out a bit. So let's go back to our first principles definition off to the left here. We have the limit as h approaches 0. And instead of having a and b, let's rewrite this using x plus h's and x's. So let's rewrite that. So the first part of that general form, a to the n minus b to the n, was going to be a minus b, which is, in this case, a minus b is x plus h minus x. And then we have that long bracket there. This is going to look a little tricky to rewrite, but let's give it a try. So we have the first one was a to the n minus 1 times b to the 0. I'll rewrite that. That's the same as writing a is going to be x plus h and b is going to be x. So we're going to follow that pattern. It's going to be x plus h, and then we go down by 1, so n minus 2, and our b, or x in this case, goes up by 1. And we continue that pattern until we get to the end, where we get x plus h to the power of 1 times x to the power of n minus 2 . And then we get x plus h to the power of 0 to the power of x times x to the power of n minus 1. And then we have all of that all over h. So now this is looking pretty complicated. But here's where little calculus magic comes into play. So let's write a limit definition at the very beginning. And let's figure out what's going on here. So I want to take a look at the very first bracket on the numerator of this fraction. We have x plus h minus x. Those x's, we have x minus x, so those are going to cancel. And we have h, just h. And then we divide by h as well. So really, those two just end up canceling. And we're left with that long limit definition there. Or we have that long expression there. So we have x plus h to the power of n minus 1 times x to the 0 plus x plus h to the power of n minus 2 to the power of times x to the 1 plus dot 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 plus x plus h to the power of 1 times x to the power of n minus 2 plus x plus h to the power of 0 times x to the n minus 1, x to the power of n minus 1. So now we've gotten rid of the h, which is the magic rule for first principles. Once we get rid of that h, we can just plug in 0 for h and we can start solving. So let's go term by term and let's see what happens. So in the first term, it's x plus h. So x plus 0 to the power of n minus 1 times x to the power of 0. So in this case, we could rewrite that. X plus 0 is just x. So the n plus n minus 1 times x to the 0. And we know that's just the multiplying powers rule, so we just add up n plus 1, n minus 1 plus 0, or just n minus 1. So now we've taken that first term, we've replaced it with that. So for the second term, let's do the same thing. That becomes x plus h is x plus 0, or just x, power of n minus 2 times x to the 1. Or we can rewrite that as we can just add those exponents together. N minus 2 plus 1, or n minus 1. As it turns out, every single term that you have, you're just going to replace it. They're all going to become x to the n minus 1. So x to the n minus 1 plus x to the n minus 1. So now, all that's left to figure out is, generally speaking, how many of these are we going to have? Because if we know how many we have, we can just common factor them all, or we can combine all the like terms. So let's take a look and figure out. We need to figure out how many terms we're going to have in that second bracket. So let's look at our rule again. So when we had exponent of 2, we had 2 terms. When we had exponent of 3, we had 1, 2, 3 terms. So as it turns out, whatever our exponent is, that's going to be how many terms we have in our second bracket. So going back to this, if we're talking about this one we had, this was x to the power of n, we're talking generally speaking. So in this case, we're going to have n terms here, which means that when we combine them all together, we're going to have n of these x minus 1 terms. So we have, this is the x to the n minus 1 term, and we have n of them. So it's going to be n to the power of x to the n minus 1. So now we've shown using first principles that this power rule actually does in fact work. It's a little bit convoluted, but now we've shown definitively that this works, and now you can use this without worrying that we're just making an assumption about this rule. So now we know it definitively works for any number.